Did Lindsay ever get that figure last night?
Yeah, I'm probably gonna do Spider.
Or the band? You said she was gonna work on it during the summer.
That was the community that we did. So I'm very pleased on this final. Monday. Also on Thursday.
Huh?
There's the final for this class.
Yep.
That yet.
Okay. I believe you. I think I had it in the syllabus correct. Is it? Did I not?
It is not.
Oh.
But
Oh, that's I didn't put a full schedule for this one because I'm making it up as I go along. But so it's on Monday of finals week, and you're
reactor lab and fuel cycles are back to back.
I'm sorry.
No.
I'm sorry. Yeah.
You got reactor exam at this lab.
Well, it's Wednesday, Thursday.
No, for
Yeah.
this class.
No, yeah. You have two exams with me in one day. Yeah, I'm sorry about that, but it makes my life easier because then I can be out on Thursday.
I did not work going straight from lab to, I got the notification and I checked, like, I checked the schedule on, I was like, oh, when's our exam for reactor lab?
Oh,
And then we have fuels like the next day.
Is.
Yeah, it's either the day before or the day after.
Oh.
And then, no, fuels like, the tenth is Tuesday, Thursday.
Wait, isn't like the.
That's when this works. Or, no, it's Tuesday.
Yeah.
So then we have it the Wednesday.
So literally all these exams are hit right before.
Yeah, and I haven't had a single exam.
Okay, so last time we talked about a specific system and one that you've probably looked at in a little bit more depth as you started the homework. So there's homework due tonight, right? The worksheet, right, where you got to play with this random walk problem a little bit more in depth. Hopefully you find it interesting, and hopefully by the time you get to reactor theory, if you haven't already been there, you'll remember the hyperbolic sign showing up as this weird business with changing exponentials around. Okay, so the way I wrote that worksheet is basically I was exploring the topic myself, and I think what will happen in the future is some of that verbiage, although maybe it belongs in a worksheet like that, that might actually just get transferred into the reading material, right, to help support the topics in the class, similar to what you would have seen early on and what we'll see some of today. So the reading for today, and I posted this on for lesson 10. Notice that if we were counting by lecture days, today would be lesson 11, right? But because last Tuesday I gave an overview of the first project, I'm not calling that a lesson. I'm trying to keep with the materials, so bear with me on that. Okay, the readings actually take you back to the 400 materials, and this would have been in ME 400, I think, lecture 21, and it served primarily as a review to what folks would have had in Math 551. Now, with the discussion last time on sort of origins of linear systems, and then with what I have in the reading today, I think this actually sets us up to continue on some of the stuff. So what the lesson today is all about, or focuses on primarily, is elimination, which of course is the process by which you get to row echelon form. I'm never going to touch reduced row echelon. I think that's too much work, but row echelon form is what we go. Because if you get to row echelon form, the rest is easy peasy, right? It's the hard part is getting into that form, and we'll talk about what that is and why. So take a look at this. It goes through both sort of like the by hand type stuff that I think makes sense for this material, but then it also covers some of the other tools, and I'll emphasize that later today. And then depending on how all of this linear algebra material goes, that will give me some ammunition to go back and revise and figure out if we need more basic stuff or not, right? As opposed to because you said all of you have had 551, so this is sort of a redundancy in your lives. So I'm using this as an opportunity to test things. Okay, so what I actually am calling this lesson, as opposed to just linear systems, which is kind of boring, is one matrix, many scenarios. And that sounds like a spy thriller, and hopefully you'll find it to be at least somewhat thrilling. Okay, so our focus is again on AX equal B, which is the linear system written in a form that encapsulates all sorts of balance law. That balance law from the random walk last time, but it could be a balance of forces in a truss system. It could be the balance of reaction rates in a transmutation system walking forward in time as uranium dwindles and say molybdenum rises. We also are focusing only on systems that have square matrices. You can have linear systems that have non-square matrices, but then you have either an over or underdetermined system, which is something that we're not ready to explore, or you wouldn't be ready to explore unless you've seen it before, and I'm sure some of you have. But we'll tackle that later on. But the focus today is on the basic elimination. That's probably the quintessential matrix analysis tool. And that's the thing that we need to use. So the ultimate goal is not just to solve AX equal B, but rather to explore this thing here, A equal LU. Anybody hear of this before? Yeah, so this is called a matrix decomposition. And there are more than one decomposition. There are more than one way to write A as a combination of one or more, or two or more matrices. But this is the one that we care about for linear systems. And the reason for that is if we know what L and U are, if we're able to take A and define this L and U, then we can solve AX equal B, where A inverse B, the inverse of A, is actually represented as the inverse of U and L. Why does that matter? Well, if we were just using elimination, or more fully Gaussian elimination, we'd solve this system once and we'd get as an output the X. But there are many applications in engineering analysis where the variety of right-hand sides changes, right? Where we have more than one potential source term, right? So if B represents the thing that is perturbing the system, in our random walk case, where was B? Where did B show up? Where was it? So in the problem that you're solving for the homework and that I had went through last time, where was the only non-zero element of B?
Very bottom there.
Yeah, and what did that represent?
Probability of neutrons escaping.
Yeah, so it turns out that in that format, the problem that you're solving actually represents something more like the adjoint problem of, let's say, the random walk diffusion problem, rather than taking a neutron born at one location and then estimating where it goes. So, but if I wanted to figure out where, like what that probability is, if maybe for a different value of M, or for somewhere in the middle of the slab, maybe I have a detector both in the center of the slab and one at the right-hand side of the slab. That would be changing an element in B. Or if I have a truss system, right? You've all had statics. You might not want to think about it, but you've had it, right? And so you could set up some free body diagrams of a basic truss system, get your vertical and horizontal forces on different junctions, and set up a system of equations, right? Who thinks you could do that? I am positive you could do that. And maybe have you had statics?
Yes.
Can you take straws and tape them together to build a rigid system?
Yes.
Could you model that?
Yes.
Yeah, right. And sometimes you'd find that you can't solve it. Sometimes you can solve it. And the various forces that you can put, like if I put a weight on it, that's going to show up in the right-hand side, B, right? But if I want to establish the stability of this bridge for a train that's over here or a person walking over here, that means I'm going to have to solve the system for a variety of right-hand sides, a variety of forcing functions, a variety of signals, a variety of impulses. Yeah.
Real quick, Professor, under the lecture 10 slides, you have lecture 19 and 400. It's not the following.
Really?
Yeah.
Oh, it should be 21.
Oh.
I'll have to fix that.
Okay.
Does that really go to?
It's lecture 10 slides.
Oh, got it. Yeah.
Numerical integration.
That's weird. I must have got the slides wrong. So I'll get these slides up, then I'll just do that. Well, you got a sneak peek of something down the line. All right. So back to the slides. So yeah, our ultimate goal is to be able to do A equal LU, and we'll do that. You'll explore that in more detail in the worksheet, which I'll have done later today. But I'll push that deadline to Sunday again to be flexible. Okay, so a variety of objectives. I said a bunch of those out loud, and then the key terms, as is typical. Right. So matrix vector products are probably the most important of the matrix and vector operations that are out there. You've learned about dot products. In fact, in the first 4 lessons, I think the 4th one in particular, there was some stuff in the reading that would have reminded you some basic matrix and vector operations. So I'm not going to review that in detail right now, but this fundamental operation called matrix vector product takes a matrix A times a vector, and what do you get? You get another vector, right? And if it's a square matrix, the vector W is the same size as the vector V. So for a 3x3 system, this looks as follows. Okay, so I'm using a pretty common indexing scheme here where I have I and J in the lower right-hand indices, and I'm using 0 as my starting point. Why? Well, because I was very particular at one point and I wanted all my math to look like my Python code. So if I mess that up and I show you something starting with 1, I apologize, right? But that's actually one thing that was important. If you use a language that is 0 indexed and you are used to counting from 1, which is usually how we're taught, like for indexing and things, you just have to be aware and get used to it. Okay. So I guess you use that as a warning or a recommendation. Okay. So we've got this matrix vector product and we know how to compute. Right. This gives you the like by example definition for how to perform a matrix vector product. You take each element of the first row of A multiplied with each element of this vector V, and that gives you the single element of the output vector W. Okay. So in that sense, the matrix vector is a sequence of dot products because this thing here, the A00 V0 plus A01 V1 plus A02 V2 is the dot product of first row of A with V. Yeah. Okay. But if you look also at this and forget for a moment that you're so hyper focused on dot products, what do we see here in this vector W? What am I highlighting? What is that value? We have a whole column that is V naught, right? Which means it's just a scalar value. And then what do I have here to the left of my hand? I have A00, A10, and A20. What does that represent? Well, they are values from the original matrix, but if I could, is that a row of A? It's a column of A, right? So I have A00, A10, A20. That is the first column of A. That means I have the first column of A times the first element of V. And then by example, you have a second column of A times the second element of V, and then so on and so forth. This is the other way of viewing it. And I mentioned this in passing last time. You can view matrix vector as a sequence of dot products, and that's a good way to compute it. Sometimes I think that, like for me anyway, that's the default way that I compute the right-hand side. But you could also compute it as a sum of the columns of A, weighted by those elements of V. Okay. Both are totally fine. You could compute that vector W using either approach. You could code it up in both ways. The result will be the same, but the utility of the methods differs, I guess, in understanding why linear systems work or don't, why a linear system can be solved or not, say. Does anybody feel uncomfortable with the basics of like a matrix vector product or a dot product before that? Okay, I'm sort of taking that as a given at this point. All right, so each element of W is a dot. So if I wanted to take one of those rows of W or one element of W from the previous slide and put it in math, it would look like this, right? I'm taking for one row of A, that would be the first row, let's say I equals 0. I would go for all column values, J equals 0 all the way through n-1, and that could be written also like this, right? So the transpose of the ith column with V, which this is called the dot product. Right? I could also write this as A sub I colon. So has anybody seen this notation before? I colon? This is something that, well, I think maybe I first saw it when folks were kind of like writing math equations in the context of MATLAB, but it works equally well for Python because slicing works the same in Python and MATLAB. So question?
It's, you know,
Yeah, so it's just like we did with NumPy arrays. Using the colon lets us take chunks of a given sequence. And if we just have a colon, so if I have a matrix A and I have I comma colon, that means the I row and then all of the columns. So it extracts out just that one row vector. So that's what the notation means here. Okay, I could probably get it. Some folks would just write this as A sub I, meaning the I row. I like it in this form because the I with the colons indicates that this is still two-dimensional, and I'm just pulling out that one row. The other notation, of course, would be if I did this, and I can just do that on the fly. If I have equal math bold font A I colon C dot math bold font B, right? That would be sort of a traditional dot product nomenclature, but all of these expressions are equivalent. Okay. And both they go by both the name dot product, which is what I typically use, or inner product. Dot product makes more sense for vectors. Inner product, a dot product is an inner product, but inner products are actually a larger class of things. It's not just limited to vectors. All right, so here I've got a function for performing a matrix vector, right? And we can use that for this exercise, okay? So I didn't get the slides to you, but let's see if we can do this. Can you quickly do this by hand? Matrix A given here and this vector B. Yeah, so let's compute W by hand. Let's warm up our brains. Okay. And then I will use it with the matrix vector, and then we'll use it with dot and with the at symbol. Let's just make sure that we can all do this by hand. So yeah, where's your pen and paper? All right, well, you type it out, then I'm gonna check. Good. I'm gonna walk around. I want to see the answer. In fact, the result is something that's worth talking about. Please, that matrix is a special one. Doesn't it look kind of familiar? Isn't it exactly the matrix that we saw last time for the case of three internal patients, right? Method. All right, so we got two of those, so I'm gonna feel like these ones. So is that a 3x3 matrix that you got on you? Right, well, this is good. I'm glad yeah, right. Do I need to go back? The previous slide? Yeah. Yeah, so I can do that. Everybody got their matrix and their vector. I'm gonna go back. So
Professor, I fear that every day is election today.
So if we struggle with this, we've already had 551.
It's like today's the day.
I'm gonna have to reflect. I think this actually modifies my homework plan for this one, so hopefully I get it to you by the end of the week, but it'll probably be released tomorrow.
Yeah,
good.
I took 551 like almost 2.5 years.
Was that?
They didn't do that. You didn't give money for.
It was a summer class, so you were trying to get through it.
Well, so yeah, so remember, if you go element or by element, it is a dot product.
Yeah.
Right, you don't necessarily require a addition. Or if you do the matrix vector, then, what, I see a chat. Yep, all right, good.
Like insanely sitting.
All right, so I think I saw the right answer on several papers. -1, 0, -1. Yep. So let me actually do this, get rid of hide. The Zoom can be so annoying sometimes. All right. So got my matrix defined. Now notice I'm just using regular NumPy arrays. NumPy does, I think, have something called a matrix, but it doesn't play nicely with arrays. So I don't know if I might point that out in the reading. All we'll ever use are the NumPy arrays unless directed otherwise. Okay. So I've got A and I can multiply it by V and I get that, right? So this is one way to do it. This is the nice way. I could also do it like this, A dot V. I get the same answer. Why would A dot? I think this is used to be the way to do it in NumPy. They added the at symbol. I mean, it's been quite a while since they've had it, but in the earliest days, it used to be this. A dot V seems like a weird way to do business. You know, a matrix vector is a sequence of dot products. So in that sense, maybe it works out because if A were a vector, then a vector dotted with another vector will be understandable. And this is just really several vectors stacked. That's one. So those are two ways to do it. And then, of course, we can check if I can still code and matrix vector AX, AV. Yep, and I get that too. So any questions on so that's a great question. In NumPy, there is no such thing as a column vector. It is just assumed, like, so if I wanted this to be explicitly a row vector, like in this case, so you can dimension it like that. So let me see if I have another. I don't have another. So if I do something like this, I'll make a new vector. So MP array, maybe MP zeros, 3 by 1. Okay, if I do that, you can see that it will show up now as an array that is vertically aligned. And if I do A at U, I will get actually, let me do ones, make it the same, right? You get the same result, but if you notice, I put retains that second dimension, like the two brackets. So you can do this. It's just, you will often have to extract elements. It makes things a little bit messy. So by default, any operation like this, if you have just a one-dimensional array without, so I can do it two ways. If I do, so U and let's say W is equal to NP ones 3 like this. Oops. Sorry. Okay. So if I do that and I do A at W, this one gives me the same thing. If I look at the W, it's exactly what I have for V. So this is, I try not to like focus on this because this is maybe not super intuitive. These are different arrays in the sense that U explicitly has a second dimension. which means if you print it out, you'll see a double set, like nested set of brackets. It really is like an explicit 3x1 matrix, which is really all a 3-element vector is. Okay, but then if I do NP1s with 3 commas, so this is a tuple. In order to make it a tuple, I've got to put that comma there, and then I get the right shape. The matrix multiplication does not care. I think I have run into issues where if I try to use this explicit shape, I start to really dislike it. So good question. Just pretend you've never thought of it. I'll look into that, and if there's like better guidance than what I just gave you, which there probably is, I'll try to bring that to class. But yeah, for our purposes, just using a regular one-dimensional array without adding the explicit 1 is the right way to do business. Yeah, that's something that MATLAB gets right. MATLAB has a real distinction between row vectors and column vectors, but that's because everything in MATLAB is explicitly a matrix. MATLAB, matrix laboratory, right? All right. So one of the things, because this lesson actually showed up much later in ME 400, there was some material that was covered earlier than that, but I think it's totally fine to just kind of explore it on the fly. I can tell you that matrix vector operations are among the most common things in technical computing, ranging from scientific simulations, right? If I'm solving, say, a massive diffusion equation for neutrons or heat or something, there is most likely a matrix times a vector, right? If you have linear systems, of course, you can do elimination, but one of the things that we'll see later on is how we can solve linear systems without inverting matrices. We actually just do something iteratively. And that iteration involves a whole bunch of these A times B. Another place where this shows up is in something that we are all becoming familiar with, and that is deep neural networks. So I'm not going to go into the details of how those are constructed, but just know that inside of these neural networks, there are matrix vector products. And in fact, the fact that they can be represented, at least parts of it can be represented that way, makes things like what is it called? It's all the stuff for the differentiation and the optimization. It's all matrix vector. Like if there's one operation that drives scientific computing, it's matrix vector. So it's probably useful to understand how expensive matrix vector operations are, right? What do I mean by expense? Yep. So how do I quantify an amount of computation that I am doing? That's a good way in practice. That's exactly what I use, right? There's actually a more fundamental unit that I can define under the hood, and I do a lot of those, and they each have a certain amount of time, right? But I have to do a lot of them in order to actually see a time. It's called a floating point operation. So if I take two numbers, A and B, and I add them together, there is something in my hardware where those numbers in their binary format are loaded into register, like actual physical silicon. And then that physical silicon has logic that will put them together, following the IEEE standard, right? With round off and things like that, because you're working with non-continuum numbers, right? You've got a finite number of bits. 64 bits is, I think, what I told you earlier in the class, right? So you've got 64 ones and zeros to represent a number like pi or 10 or whatever. The individual units on the CPU will take them and give you the result you need. It has special operations for addition and for multiplication, and in many cases, it has multiple of both. So you can actually have several of these things piling through your CPU at once. So how do we quantify the speed of a CPU? What's the typical thing you look for on your massive gaming machine? What do you want?
Your clock.
Yeah, your clock speed, right? Among the many measures that makes it good. I still play Age of Empires 2 on my PC, so I don't need anything. There's nothing that's going to help that. But with the CPUs, you typically quantify it in terms of clock speed. What's a typical value of clock speed?
4.2 gigahertz.
Yeah, gigahertz range, right? If you're fancy, you have 4.2. If you're cheap like me, you have 2 point whatever. But that's what it is. What is the unit? Hertz. And what does hertz mean? per second, cycles per second. So that CPU is taking instructions through its pipeline at a rate of 3 billion per second. Add to that some of these fancy bits of silicon that let you do additions and multiplications and so forth. You can end up with 3 billion times, say, a factor of 8, a factor of 16. So you've got billions and billions, as Trump would say, floating point operations per second on any of the machines in front of us. Okay. So how do we estimate the number of floating point operations that we can do? Well, we know what our hardware is, and then we can do an experiment and time it, and we can back out how many operations we did. That requires, though, that we can count the number of operations a given process does. That's beautiful for our case because matrix vector, easy peasy. If I go back to this slide, let's see, where's my explicit example, right? If I look at this, this is the result of my matrix times vector. How many floating point operations does this require? All right, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplications, right? Any disagreement? Okay, how many additions do I have? 6. So 15. Okay. What if I made this 4 by 4?
19, no, 20.
Well, I would go from 9
Went down.
to 16 multiplications, 25. So that's from 3 to 4. What if I went from 3 to 6?
40.
49.
Wasn't it just m plus 1 squared?
It goes as, yeah. So basically, the rule I'm looking for is if you increase the number of elements by a factor of 2, the number of floating point operations that I see over here is going to go up by a factor of 2 squared, right? So if basically the number of elements that I have in my a row of A or in my column vector V, call that n. The number of operations that I'm going to require is going to be roughly 2 times n squared, right? You lose 1 on the addition if you have 1 fewer addition per that each one of those is a floating point operation. Now, how quickly could your computer do this?
Yes.
It would be in nanoseconds, right? Because nano is 10 to the minus 9, right? Yeah, and if I have a gigahertz machine, and this is like nothing. This is very, very trivial, okay? How about if I had a matrix that was 1 million by 1 million?
30 seconds.
So if I have 1 million by 1 million, that's 10 to the 12, right?
No.
Well, maybe we should figure that out. We can play a game. All right. So one way that we can estimate time is using this thing called the time model. So here's what I'm going to do. I'm importing NumPy because I'll just start fresh. I've got my time imported. I'm going to set n, number of elements in either a row of A or the column of A to be 100. Okay. I'm making some dummy values. I don't care about the actual values. I just want to see how fast does this thing go. So I've got A is just a bunch of 1, B is just a bunch of 1. What's nice about that is you can actually compute what the right answer should be if we were doubting our implementation of matrix vector. Okay. I'm going to start off by time. So I imported from time import time. So the time module has a function called time. And what that does is it returns the number of seconds elapsed since the epoch. What the hell's the epoch? Anybody know? I think January 1st, 1970 or something weird like that. Like it's totally arbitrary, I think. So that gives us a time from some arbitrary time in the past. That alone matters not. Okay? But what we do care about is what the time is after we've done the work. Because then the difference of that time that I'm getting here from the original time is my elapsed time. And in this case, what have I done? My work is for a given number of trials, 10 trials in this case, I'm going to multiply this matrix times that vector. And I'm going to do that using my my own solution, which is going to be slower than the NumPy solution, because which is good because then we'll see this behavior as a function of the side of 10. So all I'm doing is choosing a matrix, it's vector, doing that matrix vector multiplication several times so that I get a pretty accurate timing, wrapping that in my elapsed time bit. There are other ways to do this. What's another way that I could time the computation in a given cell in Jupyter? Does it?
It tells you how long every cell takes.
Oh, yeah, okay, that's what, yeah, one option. What's another one?
VS Code is the same.
Okay, I'm looking for something that you might have explored on the homework in the past. Remember magic? Jupyter Magic, IPython Magic, there's a time one or time it, right? So you could do the same thing with that as opposed to this. I kind of like this because this also works in regular Python code. If I were to open up VS Code and want to time a certain module, right? So we're using this as an experiment to figure out how this scales. If I go up by a factor of 10 in my number of elements, how much longer does this take to work? This basic process is called profiling. It's a way to profile the time cost of a given chunk of code. This is sort of isolated. I am testing this one directly. There are tools out there though for profiling all sorts of languages. So Python has a profiler where suppose you have a full Python code, right? Like your project, and you wanted to run it and figure out where it's taking too long. You use a profiler. So maybe that's something that we'll look at later on as I sort of fill in the rest of the term. Okay, so I'm going to run this and let's see what I get. Elapsed time 3.25 times 10 to the minus 3 seconds. All right, pretty quick. I'll run it again just to see how wiggly this number is. Not too wiggly, right? If I increase the number of trials, that probably gets even less wiggly, I think, okay? But altogether, very, very quick. Now, what happens if I change that n to 1,000? What do you think is going to happen based on what we were just talking about? Thank you. Okay, so we've got 3 times, let's say 3, what is this, 3 milliseconds, okay? For the case of n equal 100. If I increase n to 1,000, what should happen to that 3 milliseconds? By a factor of 100, yeah, because I'm going up a factor of 10, so I square the 10. I'm not going up by a factor of 2, but you're right idea. Okay, so by a factor of 100, so that should be what, roughly 0.3 seconds? Yeah, so if this is 3, yeah, so 3 centiseconds, I guess. Okay, let's see. Of course, it takes quite a bit longer because I'm doing 100 trials now.
This would be about 5 minutes. We're doing 100 trials at 3 seconds.
0.3 seconds. So we can wait patiently. Come on. I want to see how many phones just came out. So I trust it'll be done in about the right number of seconds. And not full of crap. That's roughly 0.3 seconds, right? And within the wiggle that we expect. I'm going to decrease the number of trials to 10, and I'm going to increase this one more time to 10,000. Just let's make sure that we're not drawing conclusions from too few data points. What will this be, do you think? Well, I'll run it so that we're not wasting time. But what will this new number be? So if it's 3 seconds and we have 10 trials, we're waiting another half a minute. That's totally fine. That's fair of me to do that to you. 30 minutes would not be fair, but we can wait 30 seconds. Let's see. Do, 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 do. What am I doing? How does this connect to things that we've done? Your first project, how does this connect with the bottom. What is this? Is this a simulation? I wouldn't call this a simulation because I'm not simulating a given output. It's not a simulation of the physical process. Is it random? Absolutely. So this is statistical sampling. I'm taking a sample of, in this case, 10 trials of this matrix vector, and I'm computing from it. What is this? Yeah, this would be the expected time, right? I could have computed the elapsed time for every single one of these loops, right? Every time through the loop, add them up and then divide, or I can just graph the whole thing and I divide by the number of trials. I get the same answer. Uh-oh.
Seems like it's been long.
So did I mess it up? 0.33. That should be
30 seconds.
30 seconds of trial. 30 seconds. Oh,
Time's up.
so 5 minutes.
Yeah.
All right, we'll move on. You'll have to believe.
So calm.
Yeah, you'll do it on the homework. It'll be fine.
That's center.
All right, where's my stop button? All right. Huh?
Do you ever define matrix vector?
Did I ever define matrix vector? Yeah, that was up here. All right. So I'll let you explore that. The way that we would describe this is that the computational time goes as n squared or order n squared. So matrix vector n squared. Just without doing a formal study, what do you think a dot product is? If I've got a vector of n elements dotted with a vector of n elements, what do you think that would be if I were to just go by example? If I've got two numbers in each vector, how many multiplications and additions? I've got to multiply this one, and then I add them up. So that'd be 3. And if I did 4, I'd multiply them, and I've got 3 additions each. So it scales with the number of elements. So if I were, so this is for the matrix vector, but if I have a vector or dot product, then that would go as order n, right? You have to multiply each element together. That's n multiplications. And then you add up those results, which is n minus 1 additions. So it's actually 2n minus 1. What does this symbol mean? It is a symbol that's used in, I would say, theoretical computer science is probably the place where it's most often used for complexity. Basically, algorithms have complexity. Given a problem input size, how long does it take to solve the problem? In our case, the matrix vector is the algorithm. The input is the matrix and the vector, or if it's a dot product, the inputs are the two vectors. And correspondingly, the complexity, or what we turn into a practical measure of time, is encapsulated by this notation. So this means that if I go up by a factor of 2, the time will go up by a factor of 4. If I double the length of my vector that I am using for a dot product, I'll double the time. Roughly, okay, as we're seeing with these computational examples. If you had to take a guess, what happens if you go all the way to a matrix product? What do you think that'll be?
N4.
I heard n cubed and I heard n4. Thankfully, it's not n to the 4th. That would make our life a lot harder. It's n cubed. The reason for that is for the matrix multiplication. Think of the matrix multiplication as you've got a matrix times the first column of the second matrix, also times the second column. And if you've got n of those columns, all you're doing is taking the matrix vector, multiplying that by n. There are a lot of constants that we're not accounting for, but when I write something like this, think of it better as kind of proportional to, right? So for large enough n, the time will be proportional to n squared. For large enough n, the the dot product will be proportional to n. Like if matrix vector proportional to n squared, and the matrix corresponding to n cubed. So if you ever do studies kind of like what we just did, and you find that you are going worse than n cubed, there is a good chance that you have messed up, because most algorithms that we adopt in technical computing have so-called complexities that are a lot better than this. Okay, there are other things that we'll find later on, depending if we go that route, where we might have an order log n, or maybe we'll find something that has an order n log n. I'll say them now, and then we'll use them later. Log n would be like binary search, right? N log n would be something like merge sort, if I were sorting an array of n elements. Okay. But we'll move on. So the other way that we've talked about for viewing this matrix vector is as the sum of products. So I described it earlier on, but now I've actually expanded that output. So if I take my matrix A times B, now I can expand the output W as just a linear combination of the columns of A. And of course, all of those columns together represents the column space of A. Right. We'll see more about the spaces. I'm not too big on the nomenclature. I don't care about the fancy terms. I've never used the words echelon form outside of this class or the class that I had that used that form, right? So you'll see that in the reading, but all that means is that if you've gotten to the echelon form, you've gotten halfway there to the solution. Okay. So the importance of this column representation is if I have something like AX and it should be equal to B. If I have a linear system that I want to solve, that means that my X better let me represent that B. So that B has to be a combination of the columns of A. If I can't find X's to make that happen, then B does not live in the column space of A, which also means that A is not invertible. It has other properties that we don't like, right? But you can read a little bit more about that. Now, sort of the main thing for solving linear systems is elimination. And then there's also a second process called substitution. I'm going to focus primarily on the elimination. You'll get to play with the substitution. It sounds like you've all done quite a bit of this in the past, but I'll review. What does it mean to eliminate? And here's the algorithm in plain Python, right? And maybe you recognize some of the operations, right? But how would you describe it in plain English if I wanted to apply elimination or Gaussian elimination? What is that process? What am I doing to a matrix? I'll just sketch on the board my 3x3 matrix that I had before. So I have A00, A01, A02, A10, A11, A12, A12, A1, and A22. Okay, that's my matrix A. What does it mean to perform elimination on this matrix? Yeah, I make it triangular. So what do I want this to look like at the end of my adjustments?
Identity matrix.
Well, so that would take me all the way home to the solution. But the first step of that is you first turn it into triangle. And the most common way to do that is to make it upper triangle. So what we're trying to do is eliminate those the bottom left-hand elements, okay? How do we do that? Yeah, we use linear operations, linear combinations of the rows of A, okay? So what did that mean? If I wanted to get rid of A10, right? What would I need to do if I had only access to this first row here? Yeah, so if I take this row, so I'll have an A10, and then that will be what I start with, and I subtract A00, but A00 is not going to cancel that out, so I've got to have something else. Yeah. How to scale that one? And how do I scale it? I multiply. And what is that multiplier?
A10 over A00.
What is it?
A10 over A00.
A10 over A00. All right. And that, of course, would give me 0, okay? But what happens here? I have an A11, but now that's multiplied, I subtract something from that. And what am I subtracting? I have the A01, but that's multiplied by
A1, 0 over A0.
the same thing. Right? And that cancels that out. And well, actually, did I want to do that?
No, it won't cancel.
It won't cancel? Because that's not the same, it'll be something else, right? So that'll be A11 prime. A11 prime. What happens if it did cancel?
0.
Yeah, and so if it is 0, is that an issue? Could be. Could be, because if that is 0, then you have a 0 on the diagonal that usually indicates that you have a matrix that's not going to be invertible. But we'll see. Okay. And then we would, of course, do something here, and that would be an A12 prime. And that gets rid of this. And then what about the third row? Yeah, and so first of all, this would be gone to, and this would be a prime, and this would be a prime from the operations. Okay. And then we knock this out with the appropriate multiple of this. So this will end up being, now that'll go to 0, and then we'll end up with an A22 double prime. Okay, does that ring a bell? This is kind of an implementation of that. This thing here, the A00, the very first thing that we use to define this multiplier, is important and has a special name. That is called the pivot. Right, so you start off with pivots being on the diagonal. The very first one would be the 0, 0 element, and then you keep going. What happens if the pivot is 0? Which would be the case if this had been knocked out and then we were trying to go down. If the pivot is 0, you would end up in a divide by 0 situation, right? In which case you have two options. Well, you have to explore another option if you hope to keep going, and that is to permute. You switch the rows, right? There's nothing that stops me from taking my original matrix and flipping row 1 and row 2. It doesn't change as long as I change the right-hand side along with it, right? Doesn't change anything, okay? So if the pivot is 0, we have an issue. But if it's not, then everything goes out. We have the multiple, just like we defined. We subtract that multiple times the corresponding element, and what we end up with is this matrix U. So by the time we're done with this, we have this upper triangular matrix, meaning that we have non-zeros on the main diagonal and then non-zeros above the main diagonal. This thing is called U. And what is U? How does it relate to A? It's the row echelon form of A. It's your favorite thing, people, or it's at least the thing that you remembered most, okay? I don't think it's that big of a deal to call it row echelon or something. I just think of it as being the U out of the ALU decomposition. But ultimately, it is triangularizing your original matrix, right? Why do we care about this? Because if we were doing this process all along the way with the right-hand side B, so we have our X1, X2, X3 here, and then we have the right-hand side B1. Well, once we made the first switch, we would end up with a B2 prime and a B3 prime, but then we did this and we would end up with a B3 double prime. I don't know, I think that stays the same. So we've modified the right-hand side along with the original things. Why is this a beautiful system? Why, if you were given, if you suppose that every one of you were given a random 3x3 system to solve in the next 2 minutes, why would you feel like you won the lottery if you got this system, as opposed to, say, maybe the original one that we had?
Because you can easily solve for your variables in
Yeah.
in the order from X3 to X1 because it's just simple.
Yeah, I get X3 immediately. I have A22 double prime times X3 is equal to B3. Boom, I know what X3 is. If I know what X3 is, now I know how to get X2 because now I have A1 double prime times X2, the unknown. I have A12 prime times X3, which is now a known, not an unknown, set equal to B squared. I just rearrange and solve. That process of getting the solution from this system is known as substitution, or in this case, back substitution. We do a forward elimination. We go forward, knock out all these things. Once we're in this form, we can go backward. The backward part is the easy part. Why? Well, it's the same reason that if you saw this system in this random assignment of problems, you'd feel like you won the lottery. The back substitution is easy. It's that forward part that is a problem. Now, the question is, how expensive is this process? How many operations did it take for us to knock out all of those elements? Well, for one of those elements, we had a multiplication, a division, which division counts as a multiplication in our simple accounting scheme, and then the subtraction. And we had to do that for this one, and then this one, and then this one. Would you be surprised to learn that the overall complexity of this elimination step is n cubed? Because it is n cubed. It's something like 4/3 n cubed, if I remember the leading term correctly, right? And you can, if you didn't know how to do it sort of directly, what would you do to establish that? Could use an experiment like we just did before, right? But I love that kind of numerical experiment because it bypasses all of the theoretical computer science. It just gets you a number that you can feel, you can see, you can hear your computer sitting there computing for 30 seconds, this nonsense set of numbers, okay? So that goes as n cubed. Now, what about this? The back substitution. What do you think that order is? Remember, back substitution is easy. You're happy to see this because you know it's straightforward to do it. Elimination is also straightforward, but that's a lot of bookkeeping. Your gut should say, if it seems easy for me or easier for me to do by hand, then it's probably easier for the computer to do it too. So turns out that the back substitution is order n squared. Now, if you have to do a forward substitution, that forward elimination, that's n cubed, and this backward substitution, that's n squared, you're adding them together. What's the overall order of this Gaussian elimination process? If I have something that is proportional to n squared plus something that's proportional to n cubed, and I take n to be really darn big, which of those terms dominates? Yeah, the whole algorithm becomes n cubed, right? If you have any part of your program that has a complexity of n cubed, the whole thing will be n cubed. Now, depending on the size of the problem, you might never see that dependence, right? Trying to think if there's places where that shows up, but yeah, certainly in Gaussian elimination, it is the elimination step that is by far the troublemaker of it. Okay. Now, what was I doing here? I'm printing some things. Well, this is a function that we can actually see all the steps. So this matrix 3 by 3, it's the same one that we saw earlier. That right hand side 1 1 1. Well, actually, how about I do it like this? What's the answer? If I have A is equal to this matrix and I have B is equal to -1 0 -1, what is the solution to AX equal B? Yeah, exactly, because that's what you did before. You did A times X 1 1 1 gave you a right hand side or an output of -1 0 1. So -1. So if I set that as my right hand side, use the same matrix, I better get the X that we were multiplying before, which is the 1 1 1. So if I do this, let's take a look at what happens with my eliminate. I hope I didn't shoot myself in the foot and give myself a 0 pivot. All right, good. So one reason why I like, so I don't think linear algebra should be taught without code. There's plenty that I can work on as far as like the actual linear algebra stuff, but there is nothing better than the equivalent of a picture. You can learn all the algorithms and do it by hand. That's mind-numbing for sure. But to actually see the step-by-step process with output, print statements are your friend in this case. I can go from the very first matrix A. I can choose my very first element. So I'm taking that 2. Then I have to multiply the appropriate multiplier for each of these to knock out the 2 zeros. And that pivot is 2, and you can see what that output is, okay? And then it goes to the next column. That pivot is going to be what I had left over on the diagonal. It's 1.5 and then 1.33 and so forth. Now, these things here that we are computing, or the entire product, we're sort of computing those and tossing them, right? If we kept them, we would end up filling another matrix, L, that along with U gives us the A equal LU. Okay, that's what I'll have you work on in the homework, in addition to some practice. I think you'll need some practice, okay? But you'll be able to use all the code in the slides here once I get that uploaded to explore a bit further, okay? So can we reason out how the times t to perform the elimination of? We did this, right? At least heuristically. So you'll get to perform a numerical experiment just to make sure that I'm not lying to you about the n cubed. Of course, with n cubed, you got to be careful with the number of trials you do because you can swiftly go from 30 seconds to forever, right? Okay, so the elimination is the hard part. And then to fill in the gaps, we just have to do this back substitution. And here's the algorithm for that. We get the minus, you know what, I had flipped the sign on the A. It was 1 minus 2 and 1 right? What was our very first matrix? Yeah, I had minus 2s on the diagonal. Usually we have minus 2s on the diagonal when we're representing like the diffusion problem, right? Because it's like minus D times back here. Okay, we are getting close to time. Okay, there's our back substitute. So do you all see what I'm talking about? We got -1s, but that's because our matrix was flipped in sign. Was my fault. Okay. So just a quick overview of some practical things. Would you ever in the real world be expected to do elimination by hand? No. It can be useful sometimes for some sanity checks. You get a simple 2x2 system. Yeah, you should be able to do that. But in practice, you wouldn't be expected to do that, nor would you be expected to write your own code to do. It's useful here to see this elimination function because it prints out the steps. So think of that as like a learning tool. If you are actually given matrices that you needed to invert for whatever reason, you'll be using somebody else's code, somebody who specializes in that type of process. And we've already seen last time, I showed you the use of linalg.solve. And so what we can do here is read a funny word problem because this is an introductory class in programming. Let's see, Wayne Enterprises, Stark Industries, and Oscorp. Obviously, know what I like. So do we want to do this word problem? No. Right. Well, you can read it later. Here's the matrix. But here's the set of equations, and here's the matrix. We'll just get right to the story. Okay. So this is what we need to solve. You should be, so Nick, you will be the one who gets, only you on the test, you'll get this word problem, right? I'm not gonna promise because I feel like that might not be acceptable, but we'll see. So how do we solve it? Well, we solve it using either elimination and back substitution like we did before, or we can do np linalg.solve. And what this gives us is the correct number of shares of each company that we want to purchase, okay? What else could we use? What other tools do we have at our disposal for solving these linear systems? So you could use fsolve. I'm sure Arson would be happy. Right? Do you know what fsolve is doing, by the way?
Yes, Michelle.
Maybe there's part of that. It has multiple algorithms, and one of those algorithms, I think, has a guess and checks type. Yeah, it builds up a simplex, and anyway, we'll implement our own fsolve later in the class, but that would take us to a set of equations that don't fit the bill here because those would not be linear equations. Those would be nonlinear equations. fsolve handles linear equations because linear equations fall into the subset of all equations which is more broadly nonlinear. Okay. What other things do we have? Well, the other one that is easily accessible with like sort of like the default and is SciPy. Now, SciPy is adds on to NumPy. NumPy gives us the basic array manipulation capability. SciPy adds on a number of other technical computing things, but it has its own linalg module, and it has this function LU. What do you think LU stands for? Well, LU decomposition. So it will do the elimination to get us the U matrix, but it will also store this additional information to keep the L, right, for performing the backward substitution. And so if I run this, B is not defined. That should be A. That's okay. Okay. If I do, oh no, I typed A. What the hell? Okay. Oop. All right. So if I take a look at what these are, so first of all, I have this matrix P. What is P? Well, that's interesting. And I have this matrix L. First of all, what can you tell me about L? Yeah, so it is a triangular matrix, but specifically a lower triangular matrix. And what do you think U is going to look like? Upper with what along the diagonals? The pivots, right? The pivots. Okay. So what do I get if I take L times U? I get a matrix. Does that look like the matrix I have up here? Well, I haven't expanded these, but I see the 50, 45, 30, but then I see the 0, 1, and -2 at the lower row. What's happened here? Well, if I put in the P, then I get the right answer, right? Oh, no, P, uh-oh. Is it P? Well, I'm going to have to, where does the P go? P times L times U. This is embarrassing. There it is. So, yeah, all right. So if you think about what this is, when you take the inverse of a product of matrices, you flip their order. So if I wrap this in parentheses, put a -1, if I were to apply that to solve a linear system, now I have P inverse first, and then the L inverse, and then the U inverse acting on my right-hand side. What does P do? If you look at P, it's related to position, and it actually, if I take this matrix and I multiply P times A, what does that do? What's that? Yeah, it permutes the rows. This is called the permutation matrix. Why is there a permutation matrix here? Yeah, look at that. Well, I don't know if that's actually an issue by itself. I have to think about that. I don't think that's an issue, but well, actually, we can do one last quick thing here. And if I take this matrix A, that's my matrix A. If I do eliminate on A, I need B. We'll do the B here. Okay. So there was no zero pivot. So, first of all, I'll tell you the permutation is there because SciPy decided to solve the system of equations in a different order. Right? When we go through and we just continue to eliminate, we didn't make any choices over here. We just kept the rows as is and we just got rid of that lower triangle. But anytime you choose your next pivot and you have multiple rows left, you can choose which of the rows you want to serve as the pivot. So why would SciPy have changed its decision? Why wouldn't it have used the sort of, why wouldn't it have produced the same result as mine? I have a pivot 50, I have a pivot of 1, I have a pivot of -12. A pivot of 0 is bad, right? A pivot of 0 needs to divide by 0. We can't have that. But in general, pivoting by a smaller number is going to blow the number up more. The smaller the pivot, the bigger the number. the bigger the number, the more, the greater the chance of round off error there is. So what SciPy is doing here is it's taking, no matter what, we're gonna have the same three pivots. You don't change the pivots when you switch things. But what it does is it changes the order of them, and it will do the 50 first and then the 12 second, and leave this one for the very last thing where we won't have the same potential issue. Now, would it be totally fine to go in this order? Absolutely, these are totally fine numbers. But if that ended up being like 0.00001, and then you pivoted with that in the middle of all the process, you are going to introduce potentially some round off error. Remember, we only have 16 digits to work with. And if you are working with things that are like 10 to the 12, and then something like 10 to the minus 6, 10 to the 12, 10 to the minus 6, how many orders of magnitude is that? How many digits would you need to?
10 to the what?
10 to the 12,
And then
10 to the minus 6, that's 18, right? How many orders of magnitude of precision do we have? So we have 16 digits, 16 orders of magnitude. So you are automatically in round off territory if you are trying to take 10 to the 12 and add that to 10 to the minus 6. You'll add some of it, but not all the 10 to the, whatever that smaller number is, you've lost some of it. So by reordering it, you end up with a numerically more stable approach. Okay? That's and it's kind of an advanced topic. It's useful though to know why something like SciPy would give us this additional matrix P. There might be an option to tell it don't do permutations. You could look that up, but you'll get to explore this and some of the other things in the homework. So right about on time. Look for that homework. I will probably have that out tomorrow. I have like the starting point, but the exercise in the class indicates that we're going to do some review, and that'll actually help me set up some material for when I get a batch of students who hasn't had 5:15. Okay, I will see you all on Thursday.
If you go back to your vector, this wasn't like a number.
This?
2 slides back,
Thinking about it.
where you actually find it.
This. Did you use site? I only use.
Are you just copying it down?
Look at this, very funny.
Yes.
Just meeting for.
Yeah. Well.
I did all regression. You and without. Without polyfill. Here. Yeah. I do that.